let's actually work with some imaginary numbers and review how do we operate them, the basic idea that Bombelli started doing in the 16th century. And it led to, very important understanding of the imaginary unit, as I was discussing in the previous video. So let's start off with, say, 2 plus the square root of -9. First of all, how would we write that using the complex number system, using I, basically? But the basic idea is, if I was dealing with something like the square root of -9, I could kind of separate that into two components, the square root of -1 times the square root of 9. And now technically, the separation of radicals property that we know from basic algebra, it doesn't actually work with negative numbers, so you can't really do this, but it helps illustrate the idea of how the imaginary number system works. Basically, I can separate a root and think about, well, the square root of a negative, that's what I is by definition. There is no real number that can square root to make a negative, and that is what I is the imaginary unit, what the square root of -1. And then 9 itself, the square root of 9 is 3. So basically what I would get is I times 3, or more commonly we write that as 3I. And basically that is how we'd write and deal with the square root of a negative using the complex number system. And basically we could write this as 2 plus 3I. And that would not simplify, because the real component and the imaginary component won't ever add, because they're not like numbers. And I just wanted to mention that your calculator actually can do complex math. If I were to type in the square root of -9, actually, well, it can, but not if you're in the right mode. And so this brings me to an important point. Notice that when I do this, if I don't change the mode of my calculator, it gives me an error non-real answer, and I get stuck. But your calculator, if you go into the mode, notice that near the bottom, there's an option which is real, a plus bi, and re to the I theta. And basically, you can toggle the mode of your calculator from real mode. Basically, if you're in real mode, your calculator will only generate real solutions, and it will not work with the complex number system. But if you move your cursor over to a plus bi and hit enter, it will now be able to work within the complex number system. And now if I type in the square root of -9, it will actually use I and use the complex number system as we know it. And basically, I can figure that out. Or if I was to just do 2 plus the square root of -9, or I was to just evaluate the quadratic formula in my calculator, it could do all those simplifications for me. And, looking at one more, 4 minus 4i, well, 4 is again real. And then, if I'm doing the square root of a negative, also the double negative will not cancel and change to positive, because 1 is within the square root, just as a reminder. But how I would do it is, well, the negative always becomes I, the square root of 4 is just 2. So this would be 4 minus 2i if I was to write this using, again, the complex number notation. And basically, there we have it. And so what I wanted to do is practice, well, how do we deal with such numbers? Like, say we wanted to add these together, subtract, multiply, and divide. How do those work? Adding is very easy, because if I wanted to add them together, we would just add the like components. So, I could write this as, well, I have 2 plus 3i plus 4 minus 2i. And again, like, it kind of seems as though these are not, and this is just a matter of thinking, because really this is a singular number. It looks like two different numbers added together, but a complex number is really just one number. We can't bring it together because it involves those two components. And anytime we have numbers, we want to know how do we deal with them. And that's why, if I'm thinking about adding together, it behaves basically the same as a polynomial, because the two different components are entirely different. Well, the numbers will just combine. 2 plus 4 is 6, and 3i plus -2i would just be plus 1i. Basically, I can add like terms together. And if I were to subtract complex numbers, one from the other, I would need to make sure to use the distributive property, because when subtracting a compound number, both signs would change. So it would really be, well, 2 minus 4 is -2, and 3i minus a -2i, really that would be plus 2i by distributive property, or plus 5i. So adding and subtracting is pretty easy. It works just like a polynomial. And really, so does multiplication. If I wanted to multiply those two numbers, I would have to use the general FOIL principle, which also is valid for multiplication. Just like I would a polynomial. So what I would get is, well, 2 times 4 is 8. 2 times minus 2i is minus 4i. 3i times 4 is plus 12i. And then 3i times negative 2i is negative 6i squared. The one different thing about this is, well, of course I could combine like terms there and have 8 minus 4i plus 12i is plus 8i. But the last component is that I squared is something which we know I squared is always equal to negative 1. Again, by definition, since I, the unit by itself, is the square root of minus 1, and really we use I so that we don't have to write that ugly number every single time. It just is a simplification. I squared always must be negative 1 because if I were to square both sides, right, it's obvious. And so basically I can substitute in negative 1 for I squared because that is always what it's equal to. Again, assuming I is representative of the complex unit. And of course, negative 6 times negative 1 is plus 6. So 8 plus 6 is 14 plus 8i. And basically, notice that when I'm multiplying, it will still be a complex number, though the product is a little bit more complex. It's not the same combination of the numbers like adding and subtracting is. And there's a lot of interesting geometric properties behind how these numbers multiply and divide that are present within the complex plane. And that's another thing you would cover in a complex analysis course. And also to mention, your calculator can do complex math. So if you're ever like, okay, I don't remember how to do this, or you just don't want to because it kind of sucks, your calculator can do it just fine, and you can check it out that way. Now, division is kind of the most annoying of all of the operations upon complex numbers. And if you were to see this and you didn't really know where to begin, it would be easy to say, okay, I have absolutely no idea how to actually start this. Obviously, you could type it into a calculator, and it would give you the answer lickety-split. But basically, you can't really use a division algorithm because these numbers are not basic numbers like we would do in a normal division process. And you might wonder, well, can I do some sort of synthetic division or something like that? But actually, there's always an easy workaround for doing division, which is always by multiplying by what we call a complex conjugate. So if you take the complex conjugate of the denominator, and that's just a way of saying, if you take the complex number and you change the sign on the imaginary component, basically changing minus to plus or plus to minus, and that's often what we term a conjugate in math, is something where it has the opposite sign in between them. If we multiply that to the top and bottom of this fraction, it will basically do the division for us. And before I actually get into this, I wanted to talk about, well, why am I doing this? What's the value of the complex conjugate? And to get into that, we got to return back to algebra. And really, this is all resultant of a basic property which we call difference of squares. So, kind of like, remember from algebra, if you have something like this, x plus 4, x minus 4, we often call this a difference of squares because of what happens, right? When I actually multiply this through, what I get is x squared plus 4x minus 4x minus 16. Of course, plus 4x minus 4x cancel each other out, and what I'm left with is a difference of two square numbers, x squared minus 16. It's a special type of factoring where if I have x plus 4, x minus 4, sometimes you might call those algebraic conjugates, the inner term will cancel and I'll be left with just two squares. And if you actually multiply this out, you'll see why the difference of squares is important. Because, like, notice over here, when I was multiplying two imaginary numbers, what it creates is sort of like a polynomial. Something minus two terms with a single I, plus or minus an I squared. Now, if we're using difference of squares, what happens is those inner products, those inner two terms, always cancel, and that's what's going to happen here. So to summarize, if I multiply by the complex conjugate, this will turn into a real number. All the imaginary numbers will cancel. And let's just do it just so you can see what I mean. But that's always why you're using a conjugate. It's because plus something and minus something, which is all I did when I changed the sign here, always cancels out the inside parts. As just a basic property of algebra. So if I multiply this out, I'm going to get 4 times 4 is 16. 4 times 2i is 8i. Negative 2i times 4 is negative 8i. And negative 2i times positive 2i is negative 4i squared. And again, notice, well, plus 8i and minus 8i, those cancel. And that's not a coincidence because they always must cancel. And when you're multiplying by a conjugate, you can technically just skip that step and just do 4 times 4 and negative 2i times plus 2i. And notice, well, in the second component, when I'm talking about difference of squares, it always changes to a minus because positive times negative always makes negative. But in the case of complex numbers, notice that this always changes to a positive because I have negative 2i times plus 2i will be negative 4i squared. But as we know, I squared is a negative 1. So really this makes 16 plus 4, which is of course 20 in the denominator. Now I still need to figure out the numerator, and the numerator is not going to cancel because those are not conjugates. But basically, when I do all this, I'm actually solving the division, and you'll see once we finish. But on the top, I'm going to get 8 plus 4i plus 12i plus 6i squared. So that would give me 8, and this would turn into minus 6. 8 minus 6 is 2, and 4 plus 12 is 16i. So I'd have 2 plus 16i over 20. And this would be my final answer. Well, technically, I could split this up and simplify because these fractions are reducible. But I would have 2 over 20 plus 16 over 20i. And that would reduce to 1/10 plus 4/5 I. But at the end of the day, again, notice when I divide those two numbers, which I started with, I'm going to end up with, again, another complex number. It just is a fraction. And again, it shouldn't really be a surprise that I get a fraction because I'm dividing, right? When I divide, that's often what happens. It's not always pretty, but again, I can do it. It's mathematically a little bit more tedious. But again, as I said, you could always use a calculator to do the division. And let's just make sure I did not screw it up. So if I divide this with a calculator, I get 0.1 plus 0.8i. And I can always change this to a fraction by going into the math menu. And if you hit enter on the fraction, what it will do is it will turn your answer to a fraction. And I could just check to see if I actually did all that math right. But what I get is 1/10 plus 4/5 I. Cool. Anyways, that's kind of a review of complex number system and how it works. Again, we're going to get back into polynomials. I know I've been going on and on about imaginary units and how to do the math. But all of that being said, these are kind of vital components towards how imaginary numbers work. And now we're going to think about how we can work on them within a polynomial function.